the past few meetings, we have discussed a number of aspects about surface chemistry, including adsorption, catalysis, and most recently about colloids. Today, what we intend to do is to wrap up our discussion on surface chemistry with a consideration of flocculation of colloids and also about surfactants and their use as detergents. So, that will form the focus of our discussion today. So, let us start off from where we finished last class. Last class we were discussing about flocculation or aggregation of colloidal particles, and we mentioned that if you consider, let us consider a colloidal particle of whatever shape it is. Here I am considering cuboidal shape, and imagine that I break this up into two particles of this type. So, what I am doing is I am creating two surfaces here and here, and I am separating it out, and let us call this separation between these two surfaces H. So, naturally, because of interparticle forces between those that exist at the two surfaces, there is a free energy change associated with this process of shifting or breaking up this single colloidal particle into two colloidal subparticles. And flocculation is essentially, flocculation or aggregation is the reverse of this process, where two colloidal particles come together and form an aggregate. So, you could think of this as an aggregate particle and this as two particles, and this is the process that happens when colloidal particles aggregate. And we would like to understand the chemistry or the physics or the energetic requirements that are involved when such a process happens. So, if you know from your understanding of the surface tension, the Gibbs energy change when you create a surface like this will be related to the surface tension that you have got times the area of the cube that you created. So, here I have considered the simple case where the two surfaces have identical area and the surface tension is this sigma. So, if I took the case where at infinite separation, so if I plotted delta G of this, the work that is being done in creating these two surfaces, and imagine that when the two particles are at infinity, the energy is 0. So, then if you looked at this creation, as H decreases, the energy would drop because the interparticle attractive force occurs, and this is what I would see in vacuum. If I put this into a medium, and which is something that we need to consider, because if you have two particles and if you have a solvent, that is the typical situation that we are looking at. We have colloidal particles, we have a solvent, let us say water. So, we need to consider what is the effect of this medium on the work that is being done when these two particles come together, and you will find that the energy requirements are lower than this. So, you have the situation where when you have a presence of a solvent, this energy requirement is lesser. So, this from this picture it appears to us that naturally you would expect that the two colloidal particles would come together because that is energetically favorable. However, there is something else that happens. When you push these two particles together, there is also a repulsive force that exists. When the particles come close together, so this repulsive force, again as a result of what is called the bond repulsion, if you looked at this as a function of H, this energy of repulsion would go something like this. So, this is all for uncharged particles. So, what we have got is that the total energy that we have got is this delta G for this process, for this aggregation, is the sum of the delta G that we saw arising as a result of the surface area contribution, plus the Gibbs energy change that arises as a result of the repulsion. And we have got the delta G, one is this attractive force, that is from the surface area contribution, and then we have a repulsion which goes like this. And the aggregation Gibbs energy is going to be given by the sum of these two quantities. And if we consider this a little bit, depending upon the relative contributions of these two, you would have 2 or 3 possible situations. One situation is when you add these two, you will have a minimum like this, where because of the attractive contribution being larger than the repulsive contribution, you have a potential well, which means that the Gibbs energy is a minimum. And if a Gibbs energy is a minimum, what this means is that this colloidal particle has a tendency to aggregate. On the other hand, if the repulsive potential is larger than the attractive potential, if the repulsive potential is larger than the attractive potential, then you will not see a minimum and you will see it essentially go up like this. And the third possibility is where there is an interplay of these two things, and you will see a small dip and a rise, and you will have an energy barrier, and then it goes into a minimum like this. So, there are 3 possibilities, and any time you have this energy barrier where there is a good interplay of the repulsion and the attraction, that will give you a barrier towards aggregation, and that is the situation that we would like to see, because then you have colloidal particles that are stable. So, this is the situation in general that we have got. But what we have already come across, if you looked at silver iodide for example, when we made silver iodide, we said that depending upon whether you have Ki in excess or AgNO3 in excess, you will either have silver iodide colloidal particles with, in one case, I minus attached to the surface of the particle, whereas in the presence of silver nitrate you will have the other situation. You will be positively charged. So, depending upon whether you have a positively or the negatively charged species, so if you looked at the surface of the colloid, you will either have positively charged particles or you have negatively charged particles. And when you have a positively charged species like this and it is present in a solvent, naturally you are going to have compensation of this positive charge by the presence of these negative charges. And this is something that was appreciated some time ago, and this is called a double layer. And in the extreme case, you can think of this double layer essentially as two flat portions where one is a positively charged and the other is negatively charged. So, it looks similar to a capacitor. And this model is due to Helmholtz, and this is called a Helmholtz double layer. But nowadays it is appreciated that you do not have these things which are fixed. So, you will have what is called a diffuse double layer. And it is not hard to understand what this diffuse double layer is. What this diffuse double layer is if you have some positive charge like this, and that is fixed because that is fixed by the particles. On the other side, you do not have negatives all over the place. Because of diffusion of the solvent, you are going to see that it is not all negatively charged. There is also some positive charge because the ionic species will diffuse, and then across this you will see a diffusion. And this, as you go out, if you are in the bulk, then there is equal amount of positive and negative charges. So, if you plotted the potential that is formed in this double layer as a function of the distance that you have got here, it looks something like this. So, this potential has an exponential fall off. So, it will have some psi 0 e to the minus kappa times this distance z, which is understandable. So, as you go away from this point, this potential will drop, because once you have reached the bulk of the solvent, then you are not going to see any charge species, no potential difference, because there is compensation of the positive and negative charge. So, in all colloidal particles, you are going to have, because of this charge either being formed like this, or if you have charged species like in the case of proteins etc., where there is ionization, either case you are going to have charged particles, and if you have charged particles, naturally you have a potential. So, if you looked at the consideration of what is the potential that exists in this case, I have two colloidal particles in general of arbitrary shape, and there is a charged species here interacting with this charged species here, call this distance h, and everywhere I have different charge species, and what I have to do is do a summation of all the possible electrostatic interactions of these charged objects on one colloidal particle with the interaction with the charged particles on the other colloidal particle, and that is exactly what I would need to do, and this would give me the attractive force. So, this will give me the, if I looked at it rather than in the Gibbs energy, this will give me V of the attractive force that exists between these two things. And this was worked out by a person by the name of Hamaker, and this is slightly more complicated. So, what you have to see is that this is a colloidal particle and there are many charged objects here. If I had a single charged object, it is just given by the Coulomb attractive force. If I have a plus charge here, negative charge here, then I just look at the Coulomb attraction and I will get the attractive potential. On the other hand, if I looked at a colloidal particle here, then what I have got is I have charges all across the colloidal particle. Similarly, I have charged objects on the second colloidal particle, and I have to take this interaction between each charged particle pairwise and then sum this, which was done by Hamaker. And in the limit where this separation is large relative to the size of the colloidal particle, Hamaker showed that the attractive potential that you have got is of the form minus A times A over 12 times H. That is the attractive potential that you have got between these two charged particles, where H is the separation between the two colloidal particles, A is the size. So, here I am considering two spheres. The hypothetical situation where the two colloidal particles are two spheres with radius A and the distance between the two is H, and this attractive potential has this form. It is not important to memorize this form, but what is important to see is that if you plotted the attractive potential here, normally if you have intermolecular forces between two molecules, this attractive force, so for the case of the intermolecular forces, V attraction goes as 1 over r to the 6. This is something that you all know, and the repulsive force in this particular case for intramolecular forces is typically given by 1 over r to the 12. So, this is the attractive force and this is the repulsive force, where you have 2 point charges on 2 molecules. So, this is the kind of thing that we have come across, and the sum of these two gives you what is called the Leonard-Jones potential. A over r to the 6 minus B over r to the 12 will give you something which looks like this. But here what you see is, because now you have not microscopic particles, but these are colloidal particles which have much larger size relative to the molecules, and you have charges all around it. What you are now finding is this attractive potential now is of the form 1 over r, and 1 over r means that this is a long range force. This is much longer than the 1 over r to the 6 here. So, this is 1 over r when you have colloidal particles. Now, you ask the question, what is it then which is cause of the repulsive potential? And the repulsive potential comes about by cause of this double layer that we talked about. So, imagine that I have one colloidal particle like this coming near another colloidal particle which also has a double layer. So, when these two come together, the double layer on the two colloidal particles start to come together, and then there is the ions that are present in the solvent essentially cause a repulsion between these two colloidal particles. That is what happens, and that is the repulsive force that we see, and this has an exponential fall off in exactly the same way that we saw with the potential. So, in the presence of the solvent, what we are having is the charges that are present between the two double layers on the two colloidal particles start to lead to a repulsion between these two colloidal particles, which leads to a potential like that. So, this is the repulsive potential, and due to what is called the double layer interacting on the two colloidal particles, and this is nothing but the Hamaker kind of interaction between charged objects, which leads to an attractive force. So, the interplay of these two is what will determine whether you have stability or not, and we see exactly the same kinds of things that we talked about earlier. So, you will have in one situation you will have something which looks like this. If you reach this, then the colloidal particles will aggregate, whereas if this the kinetic energy. So, when you have these particles in a solvent medium, there is kinetic energy and the amount of thermal energy is proportional to kT. So, if kT does not allow you to jump this barrier, where I am plotting the potential as a function of the distance between the two particles, if kinetic energy due to thermal motion, if this quantity here is smaller than the barrier that we have got here, then we have stability for the colloidal particles. On the other hand, if the thermal energy is such that it goes over this barrier, that is, it has enough energy to pass this barrier, then it will go into this state, which is aggregation. So, that is the key to his. So, now the question is, how do I modify this double layer repulsive wall? And this is something that again is easy to understand. If I have two charged objects, and we are plotting this potential as a function of the distance away from this surface, we said that it has this form. Now, if you add an electrolyte here, the potential variation is going to be different. So, if you add an electrolyte and as you increase the concentration of the electrolyte, call this 1, if you increase the concentration of the electrolyte, this thing is going to fall off faster. So, in what we are doing is with varying electrolyte concentration, we are looking at the potential of the double layer as you go away from the surface of this colloidal particle. And what we are saying is, when the electrolyte concentration in 2 is greater than the electrolyte concentration in 1. So, when the electrolyte concentration is higher, the potential starts to drop, and if the potential starts to drop, then what happens is, in your V as a function of H, you are not going to see that barrier and it is going to go like this, which means that it would aggregate. If this were right, what we expect to see is that as you increase the concentration of the electrolyte, colloids would tend to aggregate, and this is something that you can find in this particular table. So, here is a table which gives you the concentration of the added electrolyte required for what is called coagulation, which is nothing but flocculation. And I have two different sols. I have a negatively charged silver iodide sol and I have a positively charged alumina sol, and I have listed various electrolytes and the concentration of each of these electrolytes required for coagulation of these two sols. And if you look at it, there are 3 sets in each of these two categories. In the first category, I have singly charged cation and anion, that is lithium nitrate, sodium nitrate and potassium nitrate, all monocharged. In this case, I have positively charged metal species and a monocharged anionic species, and you will find that as you went from here to here, pay careful attention to this. You look at the amount of the electrolyte required when you have singly charged species. This is of the order of 150 millimoles per decimeter cube. When you went to the di-charged species, you require almost 1/100th of what was required here for this to coagulate. And if you went, what do you expect if you go to the next one where I have triply charged positive ions? and what you find is that it drops even further. Within this, you will notice in each of these cases, you notice that there is not much difference. So, whether it is lithium, sodium or potassium, it is hardly any difference. No worthwhile difference is seen with changing of the ion, the positive ion here. So, it appears that as you change this, you are going to increase. So, when you went from singly charged ion to doubly charged ion to the triply charged ion, the concentration of the electrolyte that was required decreases as you went down like this, and the same is the case with the positively charged salt. Here again the anions may be different, but you find the same sort of trend. Ignore these small differences here, these are not significant. There are differences and that is natural to happen. Those are details that we are not worried about, but look at when you went from the singly charged to this and from here to here, that is a significant difference. And so, what we are saying is, as the charge on the ion increases, then you are going to see, in this case you are looking at the monoanion, right. So, because you have a positively charged species, you are looking at the mono charge. The monoanion is less effective in coagulation compared to the dianion to the trianion, whereas here the monocation is less efficient than the dication as opposed to the trication. And this is what is called the Hardy-Schulze law, or rule or law or whatever they call it, the Hardy-Schulze law, because these were the two gentlemen who found that as you changed the electrolyte and the charge on the electrolyte, the coagulation properties of the colloids change. As you increase the charge, the efficiency of coagulation increases. So, with this I think we will stop our discussion on the physical properties of colloids. We have looked at some of the things that we have considered in this are optical properties, where we looked at the Tyndall effect, we looked at some of the diffusion properties, that is Brownian motion, and finally we looked at the coagulation behavior of these colloidal particles. And in the rest of the time, what we will look at is an important application of surface chemistry, probably one of the most important applications of surface chemistry, and that is to surfactants. Surfactants are probably one of the biggest applications of surface chemistry, and you would have seen this in soaps and detergents. They are surface active agents or surfactants, and this is something where surface activity and surface chemistry is relevant in everyday life. And we will look at some of the properties of surfactants and how they work in the rest of the time for today. Okay. To begin with, let us give an example of what a surfactant is. A surfactant is a molecule, it is a short form of a surface active agent. If you take any surface, imagine that I have a liquid. The molecules on the surface of the liquid experience different forces than the molecules in the bulk. And this is something that we have already discussed when we talked about adsorption. So, the molecule on the surface experiences forces in all directions except the one in this direction here. There is less force there than you have forces here. So, in general, the molecules on the surface like to move from the surface to the bulk. They would rather avoid being on the surface, and this is something that we have encountered in all our lives. If you take a small drop of water and you put it onto a surface, in general the drop of water will tend to become a sphere, and the reason for this is nothing but surface tension. And any time you create a surface, you have to do work on it, and the surface tension is a measure of the work that you do to increase the area of a surface by 1 square centimeter or 1 square meter, depending upon what the units you use. So, this is easily measured. All that you have to do to measure the surface tension of a liquid is to take a microscopic slide and you dip it into this, and you can balance this with a weight, and from this you can measure what is the surface tension of the liquid. But that is not important for us. What is important for us is how we modify the surface tension of the liquid by using some properties of molecules. So, surface active agent that we typically use has a long chain fatty acid with a polar head group. So, what does this mean? So, imagine that I have a carboxylic acid of this form. This has 8 carbon atoms. You can think of bigger, and there is this carboxylic group. If I now put this in sodium hydroxide, I will form a charged species like this. Let me write this differently. Or to put it schematically, and you will have a sodium plus here. So, this is a charged head group and this is a tail. So, I can represent this schematically as a charged head group like this with a tail like this. Now, these numbers you have to appropriately match 1, 2, 3, 4, 5, 6, 7, 8. Well, I do not need this. So, I have an 8 carbon fatty acid chain and a head group, and this is charged. If I take this or something like this, I could make this long chain fatty acid even longer. So, sometimes you will see 12 carbon atoms. If you have 12 carbon atoms, this is called dodecyl. Deca is 10 and dodecyl is 12. So, you have 12 carbon atoms and a charged head group like this. If you put this into water, let us imagine. So, your solvent is water. Why am I considering water? Because I am going to use this surfactant to reduce the surface tension of water. So, if I put this into water, this fatty acid will go with its head down here and with its tail like this, and that is how it will tend to go into this. So, it will go to the surface like this, because this is the least energy structure that it could adapt. This one does not like water. It is a hydrocarbon, so it does not like water. So, it is called hydrophobic. Hydro is water, phobia means fear. So, it fears water. So, this hydrocarbon chain does not like water. So, it sticks its tail out, and the head group is a charged object. So, COO minus, and it likes water because water is a polar thing and it is ionic. So, it can ionize. So, this is something it likes. So, this one, what would you call it? If this is hydrophobic, something which likes water is called hydrophilic, the opposite. It likes water. So, if I take a surfactant, a molecule which has a long chain fatty acid with a charged head group like this, and I put it into water, it will tend to form structures like this, and when it happens, the surface tension of the water decreases. Why is it important for us to decrease the surface tension of water? Imagine that I have a cloth fiber. So, this is my cloth fiber. If I put water on this cloth fiber, if I do not have a surfactant, the water molecules or the water particles or your drop will tend to aggregate and form drops like this. Whereas, if you added the surfactant, because the surface tension has decreased, this surface now the water will flow on the surface. So, if I now draw this differently, imagine this is your surface of your cloth. If you did not have the surface active agent, the water will sit like this as drops. Now, if you have in the presence of a surface active agent, which is called a surfactant, in this case the long chain fatty acid with a polar head group, the water will spread like this. This is important. Why is this important? This is important because you could have the idea of using these surface active agents is that you want to remove dirt. So, think of this as dirt particles. So, this is a dirt particle. So, for example, grease. Grease is a hydrocarbon. Now, if I put the surfactant in here, I have to remove this dirt, and there are three things involved in detergency. So, when you look at detergency, we need three things. One is chemical energy, then we need mechanical energy, and we need, especially if you are in a cold climate, in winter you also need thermal energy, because very often you need to heat the water before you can get it off. So, these are three things that you require, and what we are trying to do is to try to do this most efficiently. So, minimize the amount of chemical energy, which is the surfactant, minimize the amount of mechanical energy. Just adding surfactant is not enough. You have to scrub the cloth together so that the dirt that is there comes off. So, you want to minimize mechanical energy, and you want to do it at as low a temperature of the water as possible. So, if you went to do it in a cold climate, you do not want to heat the water too much. So, that saves on thermal energy. So, the thing that we are looking at is essentially chemical energy. So, imagine that I have a piece of cloth here, and this is your grease. So, this is your grease particle, and we said that this is hydrophobic. So, you did something where your shirt got stained, for example, and you would like to get this off. And what we have done is we added a detergent. A detergent is like the surfactant that we talked about, except that it has when you hydrolyze this, you take this is a triglyceride it is called, and you treat this with sodium hydroxide and you will get this long chain fatty acid. This is how soaps are made. You take a triglyceride, let us imagine palmolive oil, coconut oil, whatever, you have this triglyceride, and when you add sodium hydroxide, this part gets cleaved. This part gets cleaved and you will get, oh no, wrong here, this part gets cleaved and you will get CH2OH, you will get glycerol and you will get a long chain fatty acid. It is sodium salt. Okay. So, we have this sodium salt and we put it in here. So, we will represent it. So, we are putting this in water. So, if you take this group and you put it into water, initially it will go like this, as we talked about. Now, as you increase the concentration of this long chain fatty acid, as you increase the concentration, what would happen is there is not enough space to accommodate all of this on the surface, and so you need to find some other way to do it. Then what happens is these molecules, so imagine that I have water here, then what would happen is these molecules will clump together such that the head group is on the outside and the tails are on the inside. And if you did this, this is also a stable arrangement, because what you have done is you have made sure that this portion here does not see the water, whereas the outside sees the water. So, as you increase the concentration of the surfactant, so you add a small amount of surfactant, initially it goes like this, but as you increase the concentration, it will go and form something like this, and this is what is called a micelle. So, when you increase the concentration of the surfactant, so as you increase the concentration of the surfactant, then a point is reached when the surfactant forms micelles, and the concentration at which this happens, or the range of concentration at which this happens, is called the critical micelle concentration. Or CMC for short. Now, this is useful. Imagine that I have a grease particle. So, this is my grease, and grease is hydrophobic. So, when I put the surfactant and I have enough surfactant to form a micelle, all my surfactant molecules will go like this. So, the micelle has gobbled up the grease particle. This grease and the hydrophobic chain have the same kind of interaction, they like each other. This does not like water, hydrophobic does not like water, but it likes the grease. So, it has taken the grease into it, whereas the hydrophilic head group likes water. So, what has happened effectively is that the micelle which the surfactant makes has gobbled up the grease and it has formed a clump, and you have the hydrophilic head groups sticking out in the water. So, this is sticking out into the water. So, this interaction between the water and the head group is favorable. This interaction between this hydrophobic chain and the grease is also favorable, and this is all, the grease is sticking to your fabric. Now, once this is there, you can remove the grease particle with the surfactant micelle by mechanical. So, that is where the mechanical energy comes in, because just engulfing the grease particle into the micelle is not enough. You need to then scrub it to remove this, and that is how this detergency works. So, there are various interactions that are involved. So, if you thought about this, if this is your surface, so this is your fabric, the fabric is, call it solid, then if you put water here, there is an interaction between the solid and the liquid. So, there is an interface between the solid and the liquid. If you have grease here, then there is an interaction between, so this is grease, so there is an oil solid interface. So, between the solid and the oil, that is grease I call as oil, and there is an interface between the oil and the liquid, this one here. So, there are three kinds of interaction: the solid liquid interface, the solid grease interface, and then there is the oil liquid interface, and it is an interplay of the surface tension of these three interfaces which lead to this surfactant acting as a detergent. So, with this I think we will conclude our discussion on surface chemistry, and like we said, concluding, I will just summarize what we have learnt. We said the surface chemistry that we have discussed has primarily focused on three things. We focused on adsorption, which was the initial portion where we discussed the Freundlich isotherm and things of that nature. Then we discussed one application of surface chemistry in catalysis, and we briefly discussed colloids and some of their applications. So, that constitute pretty much the three major areas of surface chemistry which we have discussed in about 6 meetings. So, thank you very much.